Welcome. Today we are going to tear apart a dense textbook chapter and rebuild it into a clear, exam-ready guide on the molecular diagnosis of tuberculosis. We're going to focus laser-sharp on the high-yield topics that pop up again and again in postgraduate exams, giving you all the depth you need to absolutely nail those 10-mark questions.
All right, here's our game plan. First, we'll see why we even needed this revolution. Then, we're hitting the two heavyweights you absolutely have to know, CBNAAT and LPA. After that, we'll clear up what the heck NAT actually means, peek into the future with whole genome sequencing, and wrap it all up by seeing how this all fits together in the clinic. Let's get to it.
So, let's set the stage. Why did TB diagnostics need a complete overhaul? Honestly, it all came down to one thing: time.
Look, the old way was painfully slow. With smear microscopy, you were basically flying blind, missing a ton of cases. And yeah, culture is the gold standard, but waiting up to 8 weeks for a result? That's a disaster. You're telling a sick patient, we'll know for sure in 2 months. For 2 months, they're getting sicker, and worse, they could be spreading it. It was unacceptable. Then came molecular tests, the NATs, and they just shattered that old paradigm. The real magic here isn't just the fancy tech. It's that we crushed that dangerous waiting period from weeks down to a couple of hours. That means we can get the right drugs to the right person right now.
Now, the engine driving all of this is, of course, PCR, the polymerase chain reaction. You can just think of it as a molecular photocopier. It's a quick cycle, really. You heat the DNA up to about 94 degrees to split the strands apart. Then you cool it down so these little starter sequences, the primers, can latch on. And finally, an enzyme called Taq polymerase comes in and builds a new copy. You do that 30 or 40 times, and boom, you've got an exponential explosion of copies, turning a single strand of bacterial DNA into millions, which is more than enough to easily detect.
All right, let's get into our first, and I mean most important high-yield topic, CBNAAT. This thing is an exam favorite. If a 10-mark question on this shows up, you need to be ready to deliver the perfect answer. So, let's build that answer right now.
And here it is, the machine that changed everything, the GeneXpert. It runs what's called the Expert MTB/RIF assay. The absolute genius of this system is its sample-in, answer-out design. See, before this, molecular testing was a huge pain. It was complicated, needed a special lab, and highly trained people. GeneXpert packed all that complexity into one simple automated cartridge. It basically took TB diagnosis out of the research lab and put it right where it's needed, close to the patient.
Now, for your exam, this definition is pure gold. Let's break down the keywords. It's automated and cartridge-based. That means fewer errors and it's safer to handle. It uses real-time nested PCR. That nested part is key. It means there are 2 rounds of PCR, which makes it incredibly sensitive and specific. But the real showstopper? It does 2 critical jobs at the exact same time. It tells you, yes, this is TB, and, by the way, it's also resistant to rifampicin.
So how does it actually see the resistance? It's really clever. The test hones in on this tiny part of the RPOB gene called the RRDR. Why there? Because that's the hotspot. It's where almost all the mutations that cause rifampicin resistance happen. The machine uses these things called molecular beacons. Just imagine 5 tiny light bulbs that are designed to stick perfectly to the normal gene sequence. When they stick, they glow. But if there's a mutation, it messes up the fit. The probe can't stick properly, the light goes out, and the machine knows. No glow means resistance. Simple as that.
And the workflow? For the person running the test, it's almost ridiculously simple. You take the sputum, mix it with a liquid that makes it safe and runny, pipette it into the cartridge, stick the cartridge in the machine, and just walk away. The machine does all the heavy lifting. It filters, it washes, it uses ultrasound to crack open the bacteria and get the DNA out, and then it runs the PCR. Less than 2 hours later, it spits out a result. It's incredible.
Okay, this slide is perfect for revision. The pros are obvious game changers. It's fast, accurate, and safe. That dual detection is the superstar, right? Knowing about RIF resistance on day 1 is huge. But for your exam, you have to talk about the limitations. It needs stable electricity and a cool room, which can be tough. And clinically, there are 2 massive points to remember. First, it detects all DNA, live or dead, so you can't use it to see if treatment is working. And second, and this is a big one, it can't see isoniazid resistance. It's a great flag for MDR-TB, but it doesn't give you the full picture.
And you can't talk about GeneXpert without mentioning its cousin, TrueNat. It's another WHO-endorsed NAT. The easiest way to think of it is as a portable, battery-operated version. The science is similar, chip-based PCR, but the key difference is its ruggedness and portability. This design is an absolute godsend for smaller health centers,
for places where the power grid is unreliable. It's what's taking molecular diagnosis to the most remote corners of the world.
All right, let's shift gears to our next high-yield topic, the line probe assay, or LPA. This is another exam regular. Now, if CBNAAT is our frontline detector, think of LPA as the specialist that gets called in next. It gives us a much more detailed map of the resistance profile.
And this right here is the heart of the test, the physical DNA strip. This is what you actually look at. At first glance, it might seem a bit intimidating, but trust me, the concept is really straightforward. The pattern of colored bands that shows up on this strip is like a barcode for drug resistance. Each line tells you something about the bug's genetics, and reading that pattern tells you exactly which drugs are not going to work.
So, for your exam, the principle is basically a two-step dance. Step 1 is familiar. You use PCR to make millions of copies of the important resistance genes. But for step 2, instead of using glowing probes, you take all that amplified DNA and you wash it over this special nitrocellulose strip. The strip is coated with probes for both the normal genes and the common mutations. The DNA sticks where it fits, and a chemical reaction creates that visible band.
Now pay attention, because this is where you can really impress the examiner. Interpreting the strip? For any drug, you're looking for one of two things to call it resistant. Either the normal, wild-type band is missing, meaning the good gene isn't there, or a specific mutation band appears. For isoniazide, it's even smarter, checking two different genes, CAT-G for high-level resistance and NH-A for low-level. And here's a critical clinical pearl you should mention. An NH mutation also tells you it's resistant to ethionamide. That's vital info for planning treatment.
So, when do you use which test? It's not a competition, they work as a team. Think of it like this. CBNAAT is your rapid response unit. It's the first test on the scene, giving you a fast yes-no for TB and raising that critical red flag for rifampicin resistance in under 2 hours. Once that flag is up, you call on the specialists. That's the LPA. It's a lab test that then gives you the detailed intelligence report on isoniazide and even second-line drugs. You use that detailed map to plan your full-scale assault on MDR-TB. Okay, quick terminology check. You're going to see the acronym NOT everywhere, and it can be a bit confusing. So let's spend a second just to clear up exactly what it means. It's actually super simple. Think of NAT as a big family name, like cars. It just means any test that amplifies genetic material. Now, under the cars family, you have different brands and models, right? Same here. PCR is the most famous model in the NAT family. So CBNAAT and LPA aren't something different from NATs. They're just very specific, very clever types of NATs that both happen to use the PCR engine. Okay, now let's jump into the future. A future that's pretty much already here. Whole genome sequencing, or WGS. This is another potential 10 marker, so let's get a handle on it.
So, if CBNAAT and LPA are like using FIND to look for a specific word or phrase in a book, whole genome sequencing is like reading the entire book, cover to cover. It reads the complete genetic blueprint of the TB bacterium from the patient. This gives us this incredible panoramic view of every single gene, allowing us to predict resistance to pretty much every anti-TB drug out there, all in one shot.
And this table just says it all. Look at a drug like parazinamide. It's a critical first-line drug. Our other molecular tests are completely blind to its resistance because it's caused by mutations in the PNCA gene. But WGS sees it no problem. It also sees resistance markers for ethambutol, the fluoroquinolones, everything. You get a complete resistance profile from one test that would have taken weeks and multiple different tests to figure out before. It's about getting the most precise information as fast as possible to build the perfect treatment plan.
So, we have all this amazing technology, but how do we actually use it in a smart, logical way when a patient is sitting in front of us? That's where diagnostic algorithms come in. Let's talk strategy.
This right here is your key clinical takeaway. This algorithm is revolutionary. For any patient you suspect has TB, the very first thing you do now is an upfront NAT, a CBNAAT or a TrueNat, and that one single result from that one test dictates the entire path forward. If it's TB but it's RIF sensitive, you start standard treatment. Easy. If it's TB and it's RIF resistant, you don't hesitate. You start them on an MDR-TB regimen and order follow-up tests like LPA or WGS to refine it. The whole point is to act decisively and get every patient on the right treatment from day one.
So I'll leave you with this final thought. For more than 100 years, the only way to be absolutely sure a bug was resistant was to try and grow it in a dish with the drug. That's culture.
But now, WGS can predict that resistance just by reading the genetic code, and it's getting scarily accurate. So as that prediction gets near perfect, what's the role for the slow, old culture method? Is the gold standard about to be retired? That's the question you'll be answering in your careers.